All right, picture this scenario. It is 2:00 p.m. You are in a glass-walled conference room, or maybe you're staring into the webcam for a remote loop. You're wearing your best shirt. Across from you sits a principal engineer. They have a notepad, a pen, and a look on their face that says they have seen every architectural mistake known to man.
I'm getting nervous just hearing this.
They lean forward and drop the big one. Design a scalable microservices architecture for a high-traffic e-commerce platform, and I want you to tell me exactly how you handle data access.
The dreaded system design interview. Yep. This is where careers are made or broken, right there.
Exactly. And you, being a smart, prepared candidate, you grab the marker, you sketch out your services, you draw your databases, and then, feeling confident, you draw a little cylinder between the service and the database, and you label it cache, and you think, okay, I'm safe, I've optimized it.
But that is exactly where the trap springs shut. Because that cylinder isn't an answer, it's a question. A huge, flashing neon question.
Right. The interviewer looks at that cylinder and asks, why? Why did you put it there? Why that specific type? What happens when the data gets stale? What happens when two services try to write to it at the exact same millisecond and suddenly the room gets very, very warm?
That is the moment where candidates either crumble or prove they are senior-level architects. It's amazing. Most people know what caching is. It's, fast storage. But they fail completely when asked about the trade-offs. They treat caching like some kind of magic fairy dust you just sprinkle on a slow system to make it fast.
Sprinkle some Redis on it. I think I've seen that pull request before. I might have even written it once.
We all have. We've all been there. But in a microservices environment, that sprinkle is actually a massive architectural commitment. You aren't just speeding things up. You're introducing consistency models, network boundaries, and potential failure modes that did not exist before.
So that is our mission today. We are doing a deep dive into microservices caching, strategies, topologies, and best practices. This is based on a really comprehensive guide from the DEV community. And honestly, this is the ultimate cheat sheet for that high-stakes interview.
It really is.
We aren't just going to define terms. We are going to explore the architectural decisions that separate a junior developer from a lead architect.
And we need to be clear about this. This isn't a Redis versus memcached feature comparison. This is about architectural patterns, the level above that.
I love it. So we've got a roadmap. We're going to start with the foundations, the why. Then we'll look at how we build it, the actual implementation models. Then comes the real meat of the discussion. Topologies. Where does the data actually live?
And finally, we'll do the math, literally, the probability math of data collisions.
Which is probably the most impressive thing you can bring up in an interview, right?
Oh, absolutely. If you can quote the collision probability formula from memory, you immediately stand out from the crowd. It shows a whole different level of thinking.
Let's get into it. Section 1, the foundations. If we were building a monolith, this conversation would be incredibly short.
Over in 2 minutes.
You have one database, one app, you cache the expensive queries, done. Why does microservices architecture make this so much harder?
It comes down to one word: ownership. To understand caching here, you have to respect the golden rule of microservices. It's called the bounded context.
The bounded context. This sounds like something from a philosophy textbook, but in practice, it can be painful.
It's from domain-driven design, but functionally it just means share nothing. Think of it this way. The order service owns all its order-related data. The user service owns all its user data. No other service is allowed to read into the order database and grab a record. It is strictly, absolutely forbidden.
Okay, let's play devil's advocate here for a second. If I'm the user service and I need to know the total value of a user's orders to display on their profile page, why can't I just run a quick select sum total from orders where user read equals 123? It's right there. It's so efficient.
It is efficient in the short term, but it's catastrophic in the long term. It's what we call building a distributed monolith. Because what happens when the order team decides to change their database schema? Let's say they rename the total column to total among cents, or they decide to switch from SQL to a NoSQL database like DynamoDB.
My user service instantly crashes.
Instantly.
Yeah.
And you might not even know why initially. You are tightly coupled to their implementation details. The share nothing rule protects teams from breaking each other. It enforces true independence.
Okay, fair enough. It decouples the teams, which is the whole point of microservices. But here is the cost, right? If the user service needs that order total, it has to ask. It has to make an HTTP request or a gRPC call over the network to the order service.
Exactly, and that's the fundamental shift. In a monolith, that's a database join. It takes microseconds. In microservices, that's a network hop. It involves serialization of the request, network latency, deserialization of the response.
And more latency. We call this inter-service chatter.
Chatter is such a polite word for it. It's more like a noisy open-plan office, where everyone is constantly shouting questions at each other across the room.
I've worked in that office.
We all have. And if you have a complex page load that requires data from 5 different services, and they all have to talk to each other sequentially, your latency isn't just additive, it compounds. You blow your service level agreement before you've even rendered the header of the web page.
So caching in microservices isn't just a nice-to-have optimization. It's the only way to make the architecture viable at scale. It's the noise-canceling headphones for that office.
That is a great analogy. It stops the chatter.
What?
But, and here's the part that trips people up in the interview, by fixing the latency, you break the truth.
You're talking about consistency.
I am. You are trading the one true database for several fast copies of what we hope is the truth.
Let's dig into that trade-off, because I think a lot of engineers, especially junior ones, get really nervous admitting that their data might be stale. We are raised on a diet of acid compliance, strong consistency.
Right. Atomicity, consistency, isolation, durability. It's the sacred promise of the database. If I write a record and you read it 1 millisecond later, you are guaranteed to see my change. This is great for correctness. You never, ever want your bank balance to be eventually correct.
Sorry, your $1 million deposit will show up eventually. Not an acceptable business model.
Not at all. But achieving strong consistency in a distributed system where services are spread across different servers or even different continents is incredibly expensive from a performance perspective. You have to lock things, you have to use complex consensus protocols like Paxos or Raft, you have to wait for confirmations from multiple nodes. It just kills performance.
So in the microservices reality, we usually have to lean towards the other side of the spectrum.
Almost always. We lean towards eventual consistency. This is the trade-off. We accept that for a brief window of time, maybe a few seconds, maybe just milliseconds, the data in the cache might be stale. It might not reflect the absolute latest write.
A brief window of staleness. That sounds poetic, but isn't it dangerous? I mean, let's take a real example. If I change my password and the off-services cache still has the old hash, I can't log in. That's a real problem.
That is a valid concern, and it's a great interview point. You have to contextualize the data. You ask yourself, what is the business impact of this specific piece of data being stale? For a password change, the impact is high. So maybe you don't cache that, or you have an aggressive cache invalidation strategy for it.
Okay.
But ask yourself another question. If a user changes their profile picture, and for 2 seconds, their friend sees the old picture on their timeline, does it destroy the business?
No, not at all. Nobody even notices.
Exactly. But if the entire system crashes because it's trying to synchronously synchronize that profile picture across 10,000 nodes instantly, that does destroy the business. So we trade a little bit of correctness for massive gains in uptime and speed.
Okay, so if I'm in the interview, I shouldn't apologize for eventual consistency. I should champion it as a deliberate, strategic choice.
Precisely. You frame it as, for this specific data set, I am choosing high availability and low latency over immediate perfection. You acknowledge the risk of staleness, and then you define the acceptable window for that risk. That's senior level thinking.
Love that. Okay, so we know why we're doing it. We need to survive the chatter. Now let's talk about how. Section 2, implementation models. The source material we're looking at mentions 2 big categories of storage engines, IMDG and IMDB.
Yes. In-memory data grids, IMDG, versus in-memory databases, IMDB.
To me, these sound like the same thing. They're both stuff in RAM, right? What, the big distinction?
They're both in RAM, that's true, but their capabilities and their costs in terms of resources are very, very different. Think of an IMDG products like Hazelcast or Apache Ignite as a giant distributed key value store. It's essentially a massive dictionary or a hash map.
Okay, super simple. Key, user.123, value. A big JSON blob representing Bob.
Exactly. It is designed for one thing, simple, lightning-fast lookups. You give me a key, I give you an object blob. It's very lightweight on the CPU because it doesn't know what's inside the blob. It just holds it for you.
And the IMDB, how is that different?
Think SQL in RAM. An in-memory database like VoltDB or MemSQL allows for complex queries. You can run secondary indexes, you can do joins, you can do aggregates, you can filter on attributes inside the data.
So with an IMDB, I can say, give me all users who live in New York and have ordered a pizza in the last week.
You can absolutely do that in an IMDB. In an IMDG, you would have to pull all the user objects out and then filter them in your application code, which is horribly inefficient and slow.
But there has to be a trade-off.
The trade-off is huge. The IMDB uses way more CPU and memory to manage all those indexes and query engines. It's a much heavier piece of infrastructure.
So for the interview, simple get-by-key lookups. IMDG, complex data slicing and bossing. IMDB, but be prepared to pay for it in memory and CPU. Now, let's talk about how the data actually gets into the cache and gets updated. The source outlines 3 core strategies: read through, write through, and write behind. I want to walk through the logic of these almost like we're pseudocoding it.
These are the mechanics of the cache, yeah. Let's start with read-through. This is probably the most common pattern people think of.
Walk me through the code flow. My service needs some user data. What happens?
Okay. Your service code, let's say your user service, needs data for user 123. Step 1. It calls a method, maybe cache. Get user.123.
And let's say it's a cache miss. The cache has never seen this user before. It returns null.
Right. Now, in a simple implementation, your user service would then have to go to the database itself. But in a read-through pattern, the cache provider itself handles it. The logic is inside the caching library or a wrapper you've configured. It sees the miss, and it goes to the database.
So the cache runs the select from users where ID equals 123 query.
Precisely. It gets the data from the database. Then critically, it stores that data internally for the next time it's requested. And finally, it returns the user object to your service.
So my service cone is really clean. It's just user exceeds cache. It doesn't even know the database exists.
Yeah.
The cache is an abstraction layer.
Correct. It really simplifies the application logic. But remember the interview trap we mentioned earlier regarding bounded context. This is where it can get you.
What's the trap here?
The trap is if you configure your cache to read through from another service's database.
Oh, I see. So if I'm the user service and I set up my read-through cache to automatically pull data from the orders table.
You have just broken the single most important rule of microservices. You bypassed the order service API and went straight to their private data store. You have failed the interview. You've just built a hidden, brittle backdoor into the old monolith.
Oof. Okay. Note to self. Don't steal data directly, even if you're using a cache to do it. Okay, what about write-through?
Write-through is all about consistency. When your service needs to save or update data, it writes to the cache. The cache provider then synchronously writes that same data to the database.
Synchronously. That's the key word. That means my application thread is blocked, right? It's waiting.
Your thread is blocked. The application does not get a success message back until the database has confirmed the save.
So it's safe, it's consistent, but it's as slow as the slowest link in the chain, which is usually the database, right?
Yes, it ensures the cache and the database are always perfectly in sync, but you pay the full latency penalty of the database write. You use this when data integrity is more important than raw write speed. Think financial transactions.
Which brings us to the speed demon of the group, write behind, also known as write back.
This is for when you need speed above all else. The service writes to the cache and the cache returns success immediately, instantly.
Instant gratification. The user sees that your profile has been saved. Message on their screen in milliseconds.
Yes. Then, asynchronously, in the background, the cache takes that write and puts it in a queue. Sometime later, maybe 100 milliseconds, maybe 5 seconds later, it gets around to updating the database.
I sense a but coming, a very dangerous but.
The but is data loss. Imagine the power cord gets pulled on the cache server, or the process crashes for some reason.
Okay, the server just dies.
If the cache had 500 writes sitting in its queue that it hadn't flushed to the database yet, those 500 writes are gone. They vanish into the ether. They never happened.
But the user saw success on their screen. They think their data is safe.
Exactly. That is the nightmare scenario.
Yeah.
So write behind is great for high volume, low importance things like maybe likes on a social media post or logging analytics events.
Yeah. If I lose one like, nobody cares. But don't use write behind for financial transactions or inventory management.
Your deposit was accepted. Whoops, never mind. The server crashed. Yeah, that's a bad day. Never ever use write behind for money.
All right, this is great. Let's move to the main event. Section 3, Topologies. This is what the source material calls the interview meat.
This is where you draw the boxes and lines on the whiteboard. The physical arrangement of the cache matters more than almost anything else. It dictates everything.
We have 4 main contenders here. Let's start with the absolute simplest, single in-memory caching.
This is the hello world of caching. It's as simple as it gets. You load data directly into the local RAM of the microservice instance itself.
So if I'm writing code in .NET, this is just the built-in iMemory cache, right?
Yeah.
Or a concurrent hash map in Java.
Exactly. You register the service in your dependency injection container, you use a method like getter create async, and boom, you have data sitting in the applications heap.
What are the pros? It sounds incredibly simple.
The pro is one thing: speed. Unbelievable speed. Zero network latency. You aren't leaving the process boundary. It is nanosecond fast. You are just reading a memory address on the local heap.
Can't get faster than that. So what are the cons?
The con is that it's selfish. And in a distributed world, selfishness leads to chaos and confusion.
Explain that. What do you mean by selfish?
Imagine you have 10 instances, 10 pods in Kubernetes of your pricing service running to handle traffic. Since they don't share memory, they each have their own private selfish cache.
Okay.
So pod A might get a request for a product and cache price, $10. A few seconds later, a different user hits a pod B. Pod B hasn't cached it yet, so it gets it from the DB and also caches price, $10. So far, so good.
Right, they're in sync.
Now, an administrator goes into the back office and updates the price to $12. The next request for that product happens to be routed to pod C. Pod C sees the new price in the database and caches $12.
But pod A is still holding on to $10, and so is pod B.
Exactly. They have no idea the price changed. So if I'm a user and I hit refresh on the product page, the load balancer might send me to pod A and I see $10. Then I hit refresh again and I get routed to pod C and suddenly I see $12. Then I hit refresh again.
And you're back to pod A seeing $10. That's a terrible user experience.
It's worse than terrible. We call that data skew. It's a Heisenberg bug. It's incredibly hard to debug because the behavior changes depending on which specific server your request lands on.
So is in-memory caching just useless for microservices then?
Not useless, but very narrowly scoped. It is perfect for immutable data, or data that changes very, very infrequently. Think reference data. A list of country codes, currency symbols, tax brackets for last year, things that change once a year, if that. If the data never changes, the skew problem doesn't matter.
Okay, so to fix the skew for frequently changing data, we usually move to contender number 2, distributed caching, the classic client-server model.
This is the industry standard for a reason. Think Redis or memcached. You have a separate cluster of servers whose only job is to be a cache. Every one of your microservice instances connects to this central cluster as a client.
In .NET, this would be implementing the iDistributed cache interface with a Redis connection string in your configuration file.
Precisely. You point all your pods at the same Redis endpoint.
So the pro here is obvious. Consistency. A single source of truth for cached data.
Right. If pod A updates the price in Redis to $12, pod B sees that new price on its very next request because it's looking at the same shared Redis cluster. It's a shared brain. The data skew problem is solved.
But there's a cost. We mentioned serialization earlier. Let's get into the weeds on that.
Yes. This is often overlooked in interviews. To put a complex object into a key-value store like Redis, you first have to turn it into a string or a byte array. You serialize it, usually the JSON, maybe protobuf or message pack if you're being efficient.
Then you send that byte array over the network to Redis.
And when you want to read it back, you do the whole thing in reverse. You pull the bytes over the network, and then your application CPU has to do the work of deserializing it back into a native object. That CPU cost adds up. If you are doing this 10,000 times a second, your CPU is going to be hot just parsing JSON strings all day.
Plus the network latency itself. It's fast milliseconds, but it's not the nanoseconds of local RAM. And you now have a new single point of failure. If the Redis cluster goes down, every service that depends on it is in trouble.
Exactly. So single in-memory is nanosecond fast but inconsistent. Distributed is consistent but slower and introduces a critical dependency.
Is there a weird middle ground? The source material mentions replicated caching.
Contender number 3, replicated, or sometimes called in-process caching. This is fascinating. You see it in really high-performance systems like financial trading platforms or real-time gaming backends.
Okay, how does this one work?
It starts out looking like the single in-memory model. Every node, every pod has a full copy of the data in its own RAM. But here's the magic. When you update the data on one node, the caching software itself, like Hazelcast or Infinispan, automatically broadcasts that update to all the other nodes in the cluster.
Whoa. So everyone holds a local copy, but the software keeps all the copies in sync behind the scenes.
Yes. It's a peer-to-peer model, so you get the absolute best of both worlds on reads. You get the nanosecond read speeds of local memory, because the data is right there on the heap.
Yeah.
But you also get the fault tolerance of a distributed system, because if one node dies, everyone else already has a full backup.
That sounds perfect. That sounds like the holy grail. Why don't we just use that for everything?
2 very big reasons. First, scalability of data size. Since every node needs to hold a full copy of the entire dataset, your cache size is limited by the RAM of a single server. You can't cache terabytes of data this way unless every single server in your cluster has terabytes of RAM.
Which is incredibly expensive.
Prohibitively expensive. And second, the chatter is back, but this time it's between the cache nodes themselves. Every single write becomes a broadcast to every other node.
Ah, so if I update a single price, my server has to shout it out to 50 other servers on the network.
Exactly. Hey everyone, key 123, change to this new value. If you have a write-heavy system, your nodes will spend all their CPU and network bandwidth just processing these update messages from their neighbors. It doesn't scale well at all for high write throughput.
So replicated caching is for a very specific niche, small datasets, very read-heavy workloads, and where you need the absolute lowest possible read latency.
Correct. Think of something like a feature flag configuration. Small dataset, everyone reads it, rarely changes. Perfect fit.
Okay, so we have fast but inconsistent, slow but consistent, and fast and synced but expensive and not scalable. Is there a best of both worlds option that actually works in practice?
That brings us to our final contender. Number 4, the near cache hybrid.
Near cache, it sounds cool. How does it work?
It's a clever two-tier system. You have a massive distributed cache, like a big Redis cluster or Hazelcast cluster sitting in the back. That's your backing cache or L2 cache. It holds everything. But then right on the microservice instance itself, you have a small local front cache or L1 cache.
So the really hot, frequently accessed stuff lives locally in RAM.
Exactly. When your service asks for a piece of data, it checks the tiny local L1 cache first. If it's there, that's a nanosecond local memory access. Blazing fast. If it's a miss, it then goes to the big L2 backing cache over the network, fetches the data, and here's the key. It puts a copy of it in the local L1 cache for next time.
This limits the memory usage locally because you're only storing the hot items that your specific instance has recently used.
Correct. You aren't trying to store the whole multi-gigabyte database in every pod's RAM, just the, say, 1,000 most active users for that pod. And a tool like Hazelcast has a really robust implementation of this. In the configuration, the near cache options, you describe the flow. You define your local eviction policy, usually LRU, least recently used. You set a time to live in seconds and maybe a max idle seconds before it gets kicked out.
But wait a minute, doesn't this bring back the original data skew problem? If I have a local L1 copy and someone else updates the data in the L2 backend, my local copy is now stale.
That is the complex part, and that's what makes this a sophisticated pattern. The backing L2 cache has to be smart enough to send out invalidation events. When a key is updated in the backing cache, it broadcasts a tiny message to all clients saying, hey, key 123 is now invalid. Everyone, please drop your local copy of it.
Ah, so it tells the front caches to clear that specific item from their local storage. The next time they ask for it, they'll have to go back to the L2 and get the fresh version.
Yes. It is more complex to set up, but performance-wise, it is often the winner for mixed workloads. You get the speed of local memory for your hot data and the consistency and scale of a distributed cache for everything else.
That is a solid lineup. I mean, if you're in an interview, being able to fluidly compare and contrast these 4 single, distributed, replicated, and the near cache hybrid, that's the winning move.
It shows you understand that there is no single right answer. There's only the right trade-off for the specific problem you are trying to solve.
Okay, let's zoom out a bit. We've got the topologies, the boxes on the whiteboard. Now let's talk about how we actually use them in practice. Section 4. High-level patterns. These are real-world architectural scenarios.
Right. Let's move from the how to the why in a more applied sense, solving specific problems.
The first one the guide mentions is the data sharing pattern. We touched on this with the order and product service example.
Well, let's go deeper on that. The order service needs product data, things like price, description, name constantly to build invoices, display order histories, and so on.
Right, and we said calling the product services API every single time is chatter. It's slow, and it puts a massive load on the product service.
So in the data sharing pattern, the order service maintains a read-only cache of the product data it cares about. It's essentially a local replica.
Wait, isn't that breaking the bounded context? You just told me share nothing. This sounds like sharing something.
It's a very subtle distinction, but a critical one for an interview. The order service cannot write to this data. It has no authority over it. It's purely a replica for performance. The product service still owns the master data. The order service is just holding a local copy to avoid making millions of network calls.
Ah, I see. So it avoids the API bottleneck, but we have to explicitly accept that the copy and the order services cache might be slightly out of date. It's eventual consistency again.
Exactly. And the product service doesn't even need to know that the order service has this cache. It just does its job. When a product's data changes, it publishes an event, maybe onto an event bus like Kafka or RabbitMQ saying product 5 updated. The order service and any other interested service subscribes to that event and updates its own local cache accordingly.
So it's shared data but not control. It's a pull, not a push.
Or listen, really. Yes, that's a good way to put it.
Next up, data sidecars. This sounds like a motorcycle thing.
It kind of is, conceptually. Imagine a very heavy read scenario, like user profiles. Everyone wants to read the user profile. The login service needs it, the checkout service needs it, the comment service, the forum service.
So the profile service is getting absolutely hammered with read traffic from all over the system.
It's drowning. It can't scale. So we attach a sidecar. We spin up a separate, dedicated, distributed cache. That's the sidecar. The profile service's only job is to keep that sidecar cache up to date whenever a user's profile data changes.
And everyone else, all those other services.
Everyone else, the login service, the checkout service, they just read directly from the sidecar cache. They don't touch the profile service at all.
They don't even talk to the profile service API.
Nope. They are configured to talk to the cache endpoint. This completely decouples the read traffic from the domain logic of the profile service. You can scale the sidecar cache to handle millions of reads per second, and the profile service can just chill, handling the occasional update write.
That is really smart. It physically separates the writing brain from the reading brain of the service.
Exactly. It's a flavor of a pattern called CQRS command query responsibility segregation. You're separating the read model from the write model.
And the third pattern, this one sounds a bit futuristic, the tuple space pattern.
This is for the speed freaks, the people in high-frequency trading, stock markets, real-time ad bidding, places where performance is everything.
So what makes it so different?
In a tuple space, or what's sometimes called a space-based architecture, the in-memory data grid isn't just a cache of data from a database. It is the system of record for all active processing.
So we aren't fetching from a disk at all. The disk is an afterthought.
Disk is way too slow. The entire application logic revolves around this shared in-memory space. A worker process throws a tuple, which is just a data object, into the space. Other workers are listening, they grab it, they process it, they might modify it, and they throw it back into the space for the next stage of the pipeline.
It sounds chaotic, like a bunch of processes just grabbing and throwing data around in a shared memory pool.
It's highly concurrent and ultra-fast. The data never has to be serialized to disk. But the trade-off is that you need massive amounts of expensive RAM, and managing the concurrency and transactions in that space is extremely complex. You don't use this to build a blog. You use this when microseconds of latency equal millions of dollars.
I feel faster just talking about it. But speed kills, right? Or at least speed causes accidents. Which brings us to our last big section, section 5. Dealing with reality. Specifically, data collisions.
Ah, yes. The dreaded split brain problem. Or a race condition in simpler terms.
This is where the math comes in. The source material has a specific scenario, and I want to visualize the crime scene here.
Let's set the scene. You have a product inventory count in your cache. Let's say we have 100 items in stock for a popular new phone.
Okay, 100 items. And the sale just went live.
Exactly. We're using a standard read-modify-write pattern. Two customers, Alice and Bob, click the buy button at the exact same millisecond. They are routed by the load balancer to two different service instances. Instance A gets Alice's request. Instance B gets Bob's.
Okay, instance A reads the inventory count from the cache. It gets 100. At the same time, instance B reads the count. It also gets 100.
Right. Now, instance A does its math. 100 minus 1 equals 99. It sends the write command to the cache. Set inventory 99.
The cache value is now 99.
A microsecond later, instance B finishes its calculation. It also thinks the stock was 100 because that's the value it read. So it calculates the new stock is 99. It sends its write command, set inventory 99.
And the cache value of 99 is just overwritten with 90.
We sold two phones, but our inventory only went down by 1. We have physically lost data. We now have phantom inventory that we will sell to some unlucky customer later.
And in a distributed system, you can't simply lock the database row easily without introducing massive performance bottlenecks.
Correct. That centralized locking defeats the purpose of scaling out. Now, how likely is this to actually happen? That's where the formula comes in. The guide gives us a great heuristic for estimating the collision probability.
Let's walk through it piece by piece.
Okay, it is roughly the number of instances multiplied by the update rate squared, $2 too.
Wait, hold on. Update rate squared. Why squared? That seems punitive.
It is, but it's accurate. It's squared because collisions happen pairwise. It takes two to tango, right? A collision requires at least two writes to happen at the same time. If you double the number of people trying to write, you don't just double the risk, you exponentially increase the number of possible pairs of writers that can collide. Think of it like the birthday paradox.
That is terrifying. So if an interviewer says, we are planning to double our traffic and our write rate next year, a good answer would be, okay, then we need to be aware that our data corruption rate might quadruple if we don't address it.
Exactly. That shows you understand the underlying mathematical reality, not just the code. So after that, you divide the whole thing by the cache size and then multiply by the latency of the write operation.
So to recap, instances times update rate to cache size times latency $.
And look at the denominator there, cache size. This represents the spread of your data. If you have a cache with 1 million unique keys, the chance of two people happening to hit the exact same key at the same time is low. If you have 10 keys and everyone is hammering those same 10 keys, you are guaranteed to have collisions.
So if the math says we are in the danger zone, the guide suggests anything over a 1% probability is critical. What is the fix? We can't just cross our fingers and hope for the best.
You have two main escape hatches. The first one is architectural, queuing.
So stop letting everyone write at once. Force them to get in line.
Exactly. Force them into a single file line. You send all your write requests for a specific item to a message queue, like a Kafka topic partitioned by product ID. A single consumer process reads those messages one by one and updates the cache.
You're serializing the processing. It completely kills the concurrency problem because there is no concurrency anymore.
But it adds latency. Your write is no longer instant. The second fix is much more common, optimistic locking, or what's called a compare and set CAS operation.
This is the check your version approach, right?
Right. When instance A reads the stock, value 100, it also gets a version number or an E tag. Let's say it's V1. When it tries to write back the new value of 99, its command is actually update the value to 99 only if the current version is still V1.
And if instance B beat them to it, the value in the cache would be 99, but the version would now be V2.
So the database or cache system rejects instance A's write. It fails. At that point, instance A's code has to catch that failure, reread the new value, 99 V2, and try the whole calculation again.
It's much safer, but under very heavy contention, you could spend a lot of time just retrying failed writes.
Which brings us full circle back to the start of our whole conversation. There is no free lunch. There are only trade-offs.
Smart. Okay, last part of reality. We have to clean up the mess. The cache is full. Who gets kicked out? We're talking about eviction policies.
And most people in an interview just say LRU and move on. But you need to know why you're choosing it and what the alternatives are.
LRU is least recently used. The logic is simple. If you haven't been touched in a while, you're probably not important anymore. Get out.
It's intuitive, and it's very effective for most general-purpose user data patterns. But consider TTL, time to live.
That's just a simple timer, right? Delete this key after 60 seconds.
Yes, but think about the use case. Real-time ad bidding. A bid is valid for maybe 30 seconds. After that, it is completely workless. TTL is perfect here because the data naturally rots and becomes invalid. LRU wouldn't care if the data is expired or not. It only cares about when it was last accessed.
That's a great point. What about LFU? Least frequently used.
This one is tricky. The idea sounds good. Keep the popular kids in the class. If an item is accessed 100 times, it gets a high-frequency counter and stays. But the risk is, what if those 100 accesses all happened last year?
Ah, so it's popular. Historically, it's a one-hit wonder from the 90s, but maybe nobody cares about it now.
Exactly. And often when you insert a new item, its frequency counter starts at 0 or 1. So it's at risk of being evicted immediately before it even has a chance to become popular. It can kill new trending items.
That's brutal. You're new here, you have no friends, get out.
It's a harsh world inside the cache.
All right.
And finally, there is RRR, random replacement.
That sounds chaotic and lazy. Just pick a random victim and kick them out.
Surprisingly, it's a fantastic baseline. If you have absolutely no idea what your data access patterns are, random replacement has very low overhead. No counters to increment, no timestamps to track, and its performance is often better than you'd think. It avoids the pathological edge cases of LRU and LFU.
So if I don't know what to choose, a good strategy might be to start with random, measure the past hit rate, and then maybe move to LRU if the data suggests it would be better.
That is a very scientific and senior level approach. Measure, then decide.
All right, we have covered a massive amount of ground here. We've gone from what is a microservice all the way down to calculating collision probabilities. Let's bring this home for the listener. How do we summarize all this for that final 5 minutes of the interview?
The summary is a decision tree.
Start with the domain requirements. Is the data read-heavy or write-heavy? What are the consistency needs?
Evaluate the load and scale. How many instances? What is the expected update rate? Do the collision math.
Pick the topology that fits those needs. If it's small, immutable, or reference data, single in memory is fine. If it needs strong consistency and can scale horizontally, distributed, like Redis, is your default. If it needs extreme read speed and fault tolerance for a small data set, replicated, like Hazelcast. And if you need a mix of local speed and distributed scale, near cache hybrid.
And always, always, always mention the trade-off you are making with your choice.
Balance memory cost against network latency against the need for consistency. That is the architect's job in a nutshell.
I love it. Now, before we sign off, I want to leave the listeners with a final provocative thought, something to chew on after this is over.
I've been thinking a lot about that tuple space pattern we discussed, the space-based architecture.
The one where everything lives in RAM and the disk is just a backup.
Yes. We are seeing memory get cheaper and cheaper and much, much faster. We are seeing new persistent memory technologies emerge. The lines are blurring. So the question is, are we moving toward a future where the database, as we know it, the slow disk-based system of record, becomes just an archive, a cold storage backup?
A world where the primary source of truth for all active operations is always in RAM.
It's possible. For high-performance applications, we might be moving away from the disk entirely as the primary store. Caching might start being a helper that sits in front of the database and start being the main character of the whole architecture.
That is a wild thought. The cache effectively becomes the database.
It's already happening in some industries like finance and telecom. It might just be a matter of time before it's more mainstream.
Well, there you have it. From a simple helper cylinder on a whiteboard to the potential future of all computing.
Not bad for a little interview cheat sheet.
Not bad at all. Listeners, here is your homework. Go and try to run the collision math on one of your own systems. You might be surprised or terrified by what you find.
And check your eviction policies while you're at it. Make sure you're not using LFU on trending topics.
Definitely. Thanks for diving deep with us. Good luck in that interview. We'll see you next time.